Welcome to the Quantum Gravity channel.
Thank you very much. So I will speak about the
Recording
idea.
in progress.
Yes, I will speak about the idea of fake particle and its implications, and I will mainly focus on how it is defined and how it works, the diagrammatics, because it involves a new diagrammatics, and then we will comment on its main applications and implications for physics. So the idea is as follows. It's the idea of a particle that's purely virtual, that never becomes real, and for this reason I call it fake particle or fakeon. It's a non-particle basically. It has no classical limit, it doesn't reach detectors, it cannot collapse, so it just lives in the virtual world, so-called. So normally you think of quantization as a process, a procedure that starts from something classical and returns what its quantum version. But what if there is something that doesn't have a classical limit, that doesn't have a classical counterpart, and so it is purely quantum, and in that sense you can reach it or guess it only if you start from loops and inside diagrams, we will see, to understand what happens and what you can do there. And maybe if you want to reach the classical limit later on, you will have to classicize the quantum theory instead of quantizing a classical one, and you will see its effects, and we will see some of these effects physically. So the best way to introduce is a new diagrammatics, which we will discuss extensively in the talk. And
sorry, Damiano.
Yes?
Let me interrupt you with a question here. We have an example, an earlier example, for example, in gauge theories where you have ghosts.
Yes.
They can appear depending on the gauge fixing in internal lines. They never appear on external lines.
Yes.
But if you wanted, you could compute diagrams with ghosts. They wouldn't mean anything in the gauge theory, probably.
Yes.
Is that analogous or it's different?
That is a good analogy that I will use to illustrate better what happens.
Okay.
It's different because what I will talk about is based on the diagrammatics and not ensured by the gauge symmetry, and that is the crucial part. But the idea is to have something that you can remove precisely as you remove Faddeev-Popov ghosts and the unphysical components of gauge fields. But in the usual case, you know that you can do that because of a symmetry. Here you don't have a symmetry, so you have to invent something new. But in the end, that is what you would like to get. And you will have also implications that are different from those of gauge theories. We will see violations of micro-causality and micro-non-locality, and these are the prices to pay.
Okay.
And we will see the applications to theory of quantum gravity, because you can have renormalizability and unitarity at the same time now, and the implications of that in primordial cosmology, where the consistency of this fakeon construction in primordial cosmology puts a stringent bound on the values of the various parameters that you have in the theory, and in the end you have this prediction, which is quite sharp, for the tensor to scalar ratio that people say is under measurement, and they will be giving us some values in the future, so let's hope that it will fit this narrow window. We will see where that comes from at the end. It can also be applied, the idea can be also applied phenomenologically to model building and search for new physics beyond the standard model, because fake particles can evade most phenomenological constraints that apply and limit the applicability of physical particles. You can solve or propose solutions of potential discrepancies with data. We try, for example, the muon anomalous magnetic moment. And the good thing is that this diagrammatics is very simple. It can be implemented in softwares, the softwares that are normally used to make hard computations for predictions in phenomenology. This is a good thing, because otherwise you could think that it is a very abstract construction. Instead, it can be translated into very simple terms. Other possibilities are that you can build higher spin massive multiplets that are renormalizable and unitary at the same time, which I will not talk about here. They are massive, not higher spin massless fields cannot be defined by this idea, and they are multiplets. You cannot have just one massive field like Pauli fields alone, because that cannot be solved by this construction. I mentioned this because by adding a massive multiplet to quantum gravity, you can change the behavior of the renormalization group flow at high energies. We will mention this fact, and make the theory asymptotically free. If you like to have something asymptotically free in the ultraviolet. And so that let's see the outlook of the talk. First, we will review unitarity, and we will turn unitarity in the usual diagrammatics, the Feynman prescription, into completely algebraic operations. That's something I have been looking for quite a while, because I didn't like so much to have to struggle a lot to understand unitarity, and the other principles of quantum field theory are expressed in very, very simple algebraic terms like locality, polynomiality in derivatives and fields, and renormalizability. Power counting is a very, very simple counting. And so unitarity remained a little bit too hard or expressed in a way that was hard to understand. So this is a general result, and I will split the optical theorem into many independent algebraic identities. And we will see the basic differences between physical particles, ghosts, various types of ghosts, and purely virtual particles to illustrate the new thing by comparison with the others. And so then we will perform the threshold decomposition of every diagram and its cut diagrams that are those that appear in the cutting equations that are a way to express the optical theorem. And then at that point, the switch to purely virtual particles will be rather straightforward, and we will see many examples of diagrams that we can treat explicitly. So first of all, what is unitarity? Unitarity is the statement that the S matrix is unitary. The scattering matrix S satisfies the unitarity equation, or equivalently, if you separate the identity from the amplitude, you can write it in the form of the so-called optical theorem. And by putting states, in and out states, you can have the usual statements that the imaginary part of the forward scattering amplitude is related to the cross-section for the production of all states, final states. So you have basically here a product of two matrices, a contraction of indices inside, and that brings in this completeness relation, which is the sum over the whole space of physical states. Now this is unitarity, and it is crucial that you have this sum and that there are no minus signs here, no states contributing with a minus sign, which would violate unitarity, and those are, for example, the ghosts. So this is the purpose, to prove that your theory satisfies something like that. And this is not guaranteed a priori. But what is important is that you can translate, first of all, this into diagrams, and they are so-called cutting equations, because they are much easier to manipulate and because they are identities that hold diagram by diagram. So, for example, you have an identity like this one. What is the meaning of that? G will be your diagram, or IT. G bar will be the complex conjugate of your diagram, or minus IT dagger. And then you will have a sum of same diagram, exactly the same, but cut. The C means cut in two parts. And one part will be shadowed, and that will denote T dagger. And the other part will be not shadowed, and it will denote T. And the cutting of these lines, these propagators, this cutting here, puts the lines on shell, and it gives precisely this sum. The sum of the cut diagrams translates into that kind of sum. And so basically you have a an internal virtual particle becomes on shell in this cut diagram, becomes real. So basically inside your diagram where virtual particles circulate, you can, by means of the optical theorem, read when those virtual particles circulating inside the loop can become real. And of course, if you want a purely virtual particle, that thing should not become real, never. And that means that you have to change the diagrammatics in an invasive surgical way to make that happen. Okay, so that's crucial to go inside diagrams. You cannot do anything like that at the tree level because of this reason. So let me show you the first the simplest two examples of such identities. You just take this process, which is basically the propagator with some factors in front. So this is just an identity for the propagator. And if you cut it, you will have a sum, a cross-section for the production of the virtual particle, this one that becomes now the final state there, and it becomes real. And the cut propagator is normally the on-shell part of the physical propagator. We will see by means of this same identity you can find out that this is the cut propagator. And it gives you information about this crucial thing, when a virtual particle becomes real. If you go to the bubble, for example, this is the bubble, and the imaginary part will be equal to a very similar integral. Integral on the space comes from the sum. This is another way to write those sums. But this time it is the same exact vertex, but it is rotated. You see, you have two final states here, these two lines that become real, they are put on shell, and basically that is a certain discontinuity. By means of this identity, you discover that you can learn about the production of those physical particles, the virtual particles that become physical, just by checking an analytic property, a certain discontinuity or imaginary part of the diagram of your amplitude. So let's check the consequences of these two. For example, the first one has a simple consequence. The first one is just the propagator, as we said, times two vertices, which we assume to be constant. And so you have the consequence that the real part of the propagator should be non-negative. For example, take physical particles. This is the propagator with a Feynman prescription. You can decompose it into the purely virtual part, which is purely imaginary also, and the real part, which is the on-shell part. And the on-shell part is plus a delta function, so it is non-negative in agreement with the optical theorem, and that would be the cut propagator, so the propagator that I denoted with a cut. You can consider ghosts. For example, a ghost can be obtained by putting a minus sign there. This is the ordinary ghost. You put a minus sign there, but if you put a minus sign there, you also put a minus sign in front of the real part, and so you are violating the optical theorem because of that. Well, there is another possibility, to put a minus sign there and a minus sign in the prescription. Then at the tree level, you change this sign twice, and it's okay. And with a certain construction inside loops, that I will not review here, you can match what Lee and Vick proposed for these objects.
Sorry, can I ask a question?
Yes.
To my knowledge, the Lee-Wick prescription doesn't work at higher loops.
Yeah, so the Lee and Vick prescription is still not formulated in a way that is guaranteed to work to all loop orders. I agree. And the final possibility is the one of the purely virtual particles, where you have nothing here, just nothing. You don't worry about the sign or having the correct sign because you put 0. So that's the simplest way if you want to be consistent with this inequality. You just have 0. And then it can work with both signs in front. That means, let's say that if you have plus, you are turning a physical particle into a fake one, and you have a minus, you are turning a ghost into a fake ghost. And a fake ghost can be okay. So the cut propagator here, the real part is 0. This part is 0. This is the idea. Now, these two things are peculiar with respect to the other two. Because, why? Well, because you see a prescription that is opposite to the usual one here, and here you have both prescriptions, plus I epsilon and minus I epsilon, and when plus I epsilon and minus I epsilon coexist inside the Feynman diagram, you have a lot of troubles that I described in this paper. Many troubles. You exchange thresholds and pseudo-thresholds. You violate the locality of counterterms. You will have non-local divergent paths out of nowhere. Violations of unitarity. And that is because you are insisting in integrating on energies and momenta as usual. You should not do that. So if you integrate on real energies and real space momenta as usual, then you are in big trouble here. That's why in both cases you have to find new prescriptions, as Lee and Vick suggest, or a new diagrammatics entirely. So as you heard already, the Lee and Vick construction is problematic at higher loop orders, and instead the fakeon one pursues a completely different path, and I will tell you how it works. And also the Lee-Vick prescription is not really a perturbative one, because you have to resum the widths of these ghosts to make them decay, and they disappear from the spectrum of asymptotic states only in the very strict asymptotic sense because of their decay. So it's like saying that the muon, you don't want to consider the muon in the set of asymptotic states just because it decays, and you are taking external states at very late times. So the crucial thing is the optical theorem and this identity here by using states, and not having contributions with minus signs here that could come from the ghosts, because the ghosts, as we said, has a minus sign here that can bring a minus sign there, and so that would violate unitarity. So here in the middle you want just +1, or a 0 could be okay, because but you cannot just suppress states. For example, Faddeev-Popov ghosts. Think of the Faddeev-Popov ghosts and the longitudinal temporal components of gauge fields, the unphysical components of gauge fields. If you remove them from the in and out states, that's an arbitrary thing you can always do. You can say, I do not want to consider scattering of ghosts, and that's what you do, of course. But what appears in this sum in the middle, is not something that you decide. So the question is to prove that if you remove something, if you remove states from in and out here, automatically the same get removed from the intermediate states. And then you have a projection, what we call a projection, something consistent with unitarity, a removal of states that is consistent with unitarity. And that is hard to prove. But in the case of gauge theories, that's what you can prove thanks to the gauge symmetry. So that's ensured by the gauge symmetry. There are other examples of projections, however, that do not rely on the gauge symmetry. One is the Veltman projection, which is the one I mentioned earlier, namely to not consider unstable states. See, if you remove unstable states like the muon here, and also in the middle, and then you have to use a semi-non-perturbative approach because you have to resum the propagators to have their widths inside, then it works. And this was proved in the 60s by Veltman, and is also the mechanism advocated by Lee and Vick. Or you have to define a completely new projection by means of a new diagrammatics, which is the thing that we will describe now, and that does not require to have anything decaying. It is completely perturbative, diagram by diagram, order by order, much more and algebraic, easier to also to understand, I think. So let's see how it works. We start from the tree level. At the tree level, you start from the Feynman I epsilon prescription, this is the usual propagator. You decompose it into its purely virtual part and its on-shell part. And of course, if you want something completely virtual, you remove that. That is what you do. And so you remain with this propagator. And that's what you can do for any tree diagram. If this is a fake, its propagator will be this one, plus or minus, could be 2 minus, not minus sign. If this is a physical particle, instead you will have the Feynman propagator, and so on and so forth. Let's go to loops. So to speak, and to simplify a little bit things, you can do the same. But there are some caveats and some things to pay attention to, but we will see them in a moment. So the first thing is to simplify everything as possible and one thing that you can do is to completely ignore the integrals on the space components of the loop momenta. And we work on the skeleton of the diagram because every identity will prove, which will be algebraic. It will not require the integral that you are ignoring here, will hold without that integral. So that's the first thing to note, because it is going to simplify the task a lot. You just integrate on the loop energies, but that you can also consider an algebraic operation by means of the residue theorem. It's just a substitution of integrands with a certain expression. So that's the only thing you will do. Once you have done the integral on the loop energies, then you use this identity to decompose every denominator you remain with. It will not be a propagator now because you have made some integral on the loop energies. Every denominator will be decomposed into its principal value and its delta part. And then you have to arrange the things properly, because this decomposition is not that simple. We will see that some caveats appear from the box. The bubble and the triangle are rather simple instead. And after that, you drop, if you want to define any particle or leg, internal leg, as a fakeon. For example, you have a triangle, you want this to be a fakeon, then the frequency associated with that leg, whenever the frequency associated with that leg appears inside the delta function, you drop the delta function. So you drop all the deltas, all the thresholds that would bring that virtual particle to reality. And we can show that this can be done consistently with the optical theorem, and so it is a set of operations that preserve unitarity. So it is a projection in the sense we mentioned before.
Sorry, when you say you drop all the deltas independent of what they multiply?
Yes.
So if they multiply a big expression, the whole expression goes away?
Yes, exactly. So you will see in a moment these expressions. So so we start from the Feynman I epsilon prescription. Everything in the construction starts from there. So you do not have to think of anything fancy, anything strange here. It's just the usual diagrams, and it is a surgical operation on the usual diagrams. But to simplify them, we ignore completely the integrals on the space components of the loop momenta. So, for example, this is a one-loop integral. It's just the integral of some loop momentum k of a product of propagators. You can put derivatives in vertices, but they will not complicate the final construction, so I will not put them. So you ignore completely the integral on the space components of the loop momenta and some factors for convenience, which are these. And then you have just the integral on the loop energy, okay, of some products of propagators, times some factors that I inserted for convenience. And then you integrate on the loop energies by means of the residue theorem. And you will get something. And then you proceed and you do what I said before. So before doing it for the bubble, we'll do it explicitly in a moment for the bubble, let me just tell you the notation I'm using. I will have diagrams, then there will be cut diagrams, like this is a cut triangle. And instead of using cut diagrams, I will mark the vertices that are on one side of the diagram and not mark the vertices that are on the other side of the cut, not of the diagonal, of the cut. So I can, if I cut vertically like this, I have two ways to cut, because I can interpret this thing as T dagger and this as T, or this thing as T dagger and this as T. And so I use just marked vertices, and marked vertices will be denoted by letters with dots, and not marked vertices will just be denoted by letters with no dots. So a triangle for me will be a word, ABC. The conjugate triangle will be A dot, B dot, C dot. This is a cut diagram of one type, this is the other cut diagram, and then you have three permutations. So this is just the notation. Okay, so let's see the bubble. The bubble is just two vertices, so it is AB, the word AB. And then there will be the conjugate and the two cut diagrams that we will see later. So there will be something like that. But for the moment, we just consider the bubble. The bubble is the product of two propagators. Here, you just integrate on the loop energy because we do not want to integrate on the loop space momenta. And the integral, by means of the residue theorem, gives the sum of four contributions, four denominators. Two of them cancel out, so only two remain, which are these ones. And for that cancellation, the Feynman prescription is crucial.
Sorry, Damiano, how did you go from the first integral to the second?
The second is the same. It's just I just wrote k minus p squared as the energy minus the...
Oh, I see. Okay.
Oh, I forgot to say, by the way. I put an independent momentum, P, external momentum for every internal legs. So if you have, for example, a vertex like this inside a diagram, these are internal legs. Internal legs. Then you can say there is a conservation of momentum, and so the total momentum flowing in is 0. No, I don't want that. I want every leg to be symmetrical, and I treat all the legs symmetrically, so I will put a P1 here, a P2 here, and P3 here, and a P4 here, independent. So I am assuming that there is always attached to a vertex, there is always an external, a further external leg, because that is more general. I do not need to imagine that my vertices are the vertices of a renormalizable theory, for example, that they have only 3 or 4 legs. They can have 5, 6. I can always add an imaginary external leg, external leg to flowing some external momentum. So this is going to make every expression more generic and also more symmetric. And so this is the energy of the external energy of that leg, MPA. So when you integrate here, this is a product of 4 denominators, because you have 2 propagators. Every propagator is the product of 2 objects, so you have 4 denominators. So you have 4 contributions, but 2 cancel out, and this is crucial. This is due to the Feynman I epsilon prescription. And then you decompose this. Principal, value, and deltas. And that's it. That's the threshold decomposition of the bubble. And now you say, okay, if I want a fakeon in leg 1, for example, that means that its frequency, omega 1, will be the fakeon frequency, and it appears in both deltas. Then you suppress both. And this is the result for the diagram with a fakeon. So here it is very simple, and you can repeat that for the diagram, its conjugate diagram, and the 2 cut diagrams that I mentioned earlier that are denoted by this. B is bubble, S for skeleton diagram, and not integrating on the loop space momenta. And then below I put the type of diagram, cut or not cut, by means of that notation. So in vertical you have the diagram. You use the same decomposition and residue theorem and the same operations for all of them. And then you read the table like this. Bubble is a principal value with this notation, -1 times a delta, where I include a pi here, -1 times another delta. So it is the sum of 4 contributions. The conjugate diagram is the conjugate, so you just have a conjugation in the principal value because the deltas are real. The cut diagram doesn't have principal values because you are in a cut, so you are already on shell somewhere. So there are only deltas. And you will find a 2 for multiplying this and a 2 multiplying that. So you can organize this in a table made of rows, and you see that every row vanishes independently. So the optical theorem that tells you that the sum of these 4 is 0 can be decomposed into rows, which I call spectral optical identities. Many identities that hold independently, threshold by threshold, because the thresholds don't talk to each other. And I call it spectral optical theorem because it holds for arbitrary frequencies, because I'm not integrating on the loop space momenta. And that is very, very convenient, because when you want to say, oh, I want leg 1 to be fake. If leg 1 is fake, then you have frequency 1 inside both deltas here, and you have to remove them. But you remove the entire rows. Not just inside one diagram, the entire rows, you have to. But if you remove an entire row, the optical theorem, of course, will hold, because all those rows sum up to 0 independently. And that's why these diagrammatic operations preserve the optical theorem. One thing that then happens is that after you remove those rows, you can remove some columns as well, these two, because the entries of those columns that survive are just zeros. So the entire cut diagrams disappear. And that is good, because if you want one leg to be fake, once you cut it, you have the cut propagator of a fake particle, which should be 0, because on shell the fake particle cannot exist. So it's okay to have that those columns at this point disappear by themselves. And so you remove everything and you just have a very simple reduced table. And that is the optical theorem for the fake bubble. For example, let's check the triangle. The triangle is ABC, A dot, B dot, C dot. Then there are 6 3 plus 3 cut diagrams. You can build the table the same way. So there will be, after you integrate on the loop energies, these are 3 propagators with the residue theorem, you will get a certain sum of fractions, of denominators, and then you use the decomposition into principal value and deltas, and these, the first row is the row that collects only the principal values, no deltas. And then you check the second row, or these rows are 6 because there are 6 permutations, and these contributions will be some Q. Q is just the sum of 2 principal values times 1 delta. Q, 1 delta, Q, 1 delta in all. And then we will have also 2 deltas, of course. Constant times 2 deltas. And then again, you do the same, exactly the same thing for all diagrams, all columns. Of course, the cut diagrams are simple because, for example, they don't have any principal values to begin. Anything that is just the principal value, but they can have principal value times delta and so on. And then you will see that you can decompose the optical theorem in many identities that hold independently because each row sums to 0. And that's because every different singularity doesn't talk with the others. And that is it. That is what I call, these are what I call the spectral optical identities, so the rows. So for example, I minus 2i, and then 2i, and so on. 2q12 minus q12 minus q12, and so on. Now, what happens when you want to convert one particle, let's say leg 1, into a fake? Every delta that contains its frequency omega 1 inside, so every delta with one index 1, will be suppressed, and the entire row will be suppressed as well. So the rows in red go. Delta 1, 2, delta 3, 1, all these go, and only the deltas, the rows with no ones, survive. So basically you are saying that if this is A, B, and C. If 1 is the leg that you want to be fake, then you can only cut here. You cannot cut the leg of the fake because that would give 0. That disappears. And again, when you have done this removal of rows, some columns disappear as well, because in blue you will have just zeros. So this disappears, this disappears, this doesn't disappear, this disappears, and this doesn't disappear. And those that disappear are precisely the diagrams where you are cutting the fake propagator, and the fake propagator is 0. And so in the end, you will get a surviving table which is given by the blue part, and this is the optical theorem. So these are the surviving diagrams with one fake in vertical, only 2 cut diagrams, and the optical theorem is again guaranteed because it's just a reduction of the previous one by eliminating rows and then eliminating columns that eliminate themselves for free. Okay, so far it is simple, but then I went on because I wanted to be sure, and so I studied the box, the pentagon, and the hexagon, and with the box I found some obstacle that I will describe that might be interesting for, because it's a mathematical property that I don't know people noticed before. I will illustrate it in a moment. But basically, in this transparency, I'm just telling you that once you integrate on the loop energies, you are basically replacing the triangle as we know it, the diagram as we know it, into snowflake diagrams that are ways to organize the denominators that survive after integrating with the residue theorem. So for the bubble, you have just one denominator basically, and its permutation. For the triangle, the same. And for the box, something happens because you have 2 different contractions that we will see in a moment. So let me describe the box and the new thing. Check these identities here, which are quite striking, and for some time they drove me crazy because I couldn't find. I had mismatches in the box, and I had a hard time understanding what was happening. But basically, you may think that the principal value of 1 over x is purely virtual, and that is okay, of course. And you see it in the propagator. Your propagator is the principal value plus the delta, and this is the on-shell part. But then the problem is when you have many denominators, and in complicated diagrams you have products of many denominators, and eventually you will have the principal value of a product of 2. Well, it turns out that there is a small on-shell part inside. It may be not obvious, but this is an identity. The ones I am writing here are identities that you can check numerically by means of a test function. So naively, you see this expression inside the parentheses is 0. If you sum the 3 things with a common denominator, if x is different from 0 and y is different from 0, and x plus y is different from 0, then certainly the sum is 0. But the principal value of the sum is not exactly 0, because it is actually the product of 2, not 1, 2 delta functions, one in x and one in y. And this, by the way, can be proved, this identity, with the same threshold decomposition that I just described. You just start from an identity that you write with principal values and you decompose that. And then you will, maybe you put epsilon1, epsilon2 to be different, and you can prove it that way. But if you are skeptical, just check it with Mathematica with a test function and two-variable test function to see that the two things are the same thing. With a box, it's important to use it. Let me show you why, because in the box, as I said, you have two, after you integrate on the residue theorem, you will have two snowflake diagrams, basically two ways of contracting the various denominators. FAB is the basic denominators. These are external energies, and these are frequencies with their epsilon infinitesimal widths. And you can contract them in two ways. FAB ACAD, which means that there is a common index to all, or FAB ACDB, which is the second way of contracting them. And then you use the decomposition of every denominator into principal value and delta. And you would guess that that's all. You just then enumerate the various combinations, and you have things with only principal values, things with principal values and one delta, things with two deltas, things with three deltas. Yes, that's true, but they do not come up right away. You have to do some operations because of these annoying properties. And this is the final result, by the way, after you clean the decomposition. But let me show you why you have something problematic. Because at some point you will find some strange objects. Let me remind you that delta 812 is just apart from the pi is a delta plus energies, and p instead are principal values. Okay, and you have many, of course, because it's a box. You have many contributions. You just have to be a little bit patient and collect them. The ones in red are suspicious. Let me take one in red here, this one in red, and write it explicitly. Well, you will see it that if you write it explicitly, and maybe to help yourself, you can reinsert the loop energies that we have it being integrating out, because there is a delta. It's quite kind of easy here to reinstate the loop energy. Then you will have the product of four contributions. A box has four internal legs, two deltas, two principal values, but you see that one doesn't talk with the others. You will see that basically you are generating a singularity, the zero of those four, that has nothing to do with the box. It has nothing to do with the box, because you will see that K0, the loop energy, basically stays within a triangle and leaves the fourth leg out. So basically this is something that should disappear. You are writing something badly, and you are thinking that there is a singularity that wasn't present in this diagram you started with and that you wanted to decompose, so it must cancel out. And indeed, once you sum those two, it cancels out. And it cancels because of this identity, this mysterious identity. So basically what you do is you take this expression, you add an apparently complicated expression written here, which is actually not complicated because it's the sum of principal value, principal value, principal value, principal value, principal value, principal value in a certain way, so that you can use this. See, principal value, principal value, principal value, principal value, principal value, principal value, two deltas. So, oops. So you add an expression that is just three deltas, because there is one delta out, and there are two principal values, two principal values, two principal values, which give two deltas, and the same here, which give two deltas. And then you are able to cancel completely those things and just double the ones in blue. So this will become 1 and 1. And then you clean the decomposition, because you will have a very nice a contribution with 1 delta, and then some residual contributions with 3. Okay, so that's how it works. It's kind of annoying, but in the end it's purely algebraic, as I stressed, and you have this nice decomposition of the box. You have 1 contribution with all principal values. These are the single thresholds, 1 delta and principal values, double thresholds, and triple thresholds. And then you repeat the same thing, the table with the cut diagrams, you do the same thing. You do all the cuts, and then when you want to project a fake, an internal leg to a fake, you do the thing that you know, you suppress entire rows wherever the frequency of that leg appears inside the delta function. Okay, now I describe it in very simple ways what happens in the bubble, for example, explicitly. I give you the result so you can see what the amplitude looks like, aside from the algebra that we have said so far, where we dealt only with the optical theorem and we were able to prove these identities without ever integrating on the loop space momentum. Instead, here we do the integral, and you know very well what happens in the bubble. The bubble in 4 dimensions is a logarithm, basically. I'm using here massless fields to simplify the matter, but remember that fakeons should not be massless. With massive fields, the formulas are a bit more complicated. You might remember the logarithm of minus p squared minus m1 squared x plus m2 squared 1 minus x, this kind of formulas that you know very well from quantum field theory. But in the case of massless fields, they simplify very much, so it's better for illustrating this in a talk, and then if you want, there are details in the papers. So basically, a bubble in 4 dimensions is, with a Feynman prescription, just this, a logarithm. So we imagine that the divergent part, which is also a logarithm, but it is a logarithm of a constant, has already been taken care of. This is just the bubble. So from the point of view of analyticity, as an analytic function is the logarithm. What is the fake bubble? The one where inside you have a fake. It's the same with no imaginary part. So it's just this. We will plot it in a moment because the consequences are important here. What is analyticity here? Striking is in 3 dimensions. In 3 dimensions, it's even more striking because you can appreciate what happens and the importance of what happens. In 3 dimensions, you just have 1 dimension less, so the bubble is a square root of 1 divided by square root. So this is the normal bubble. Well, if you have a fake and you apply the previous rules, you have that on the real axis. There is a threshold here, you see p squared equals 0 as a threshold. Above the threshold, you have 0. More explicitly, in 4 dimensions, this is the Feynman prescription. You have a logarithm. Well, you know what to do with the logarithm. On the positive real axis, you just have the logarithm. This is below the threshold. This is the Euclidean region. This is where we all agree what happens. And then, if you want to go above the threshold, then you have a way to circumvent. Oh, by the way, I think I forgot to correct this diagram. I have to mirror this because it's wrong here. Okay, imagine that this is this and the cut is there. I forgot to correct it. I noticed it yesterday, but I forgot. So imagine that there is a plus here. Okay. Anyway, there is a unique way to circumvent the branch point and go to the negative real axis, and you know which way. It is given by the prescription. But if you use the fakeon prescription, you know that below the threshold it is the logarithm again. Nothing changes. But above the threshold on the real axis, it is again the logarithm with no imaginary part. So it is the logarithm of minus z. And that means that you have not one analytic function, but two. And those two analytic functions cannot be analytically connected. So you must cut away a cone in your complex plane. You must divide the complex plane into two disjoint regions. So you do not have analyticity as usual, because the operations that I described, this surgical removal of deltas and so on and so forth of on-shell paths, is not analytic in the usual sense. But it is analytic, let's say, region-wise. You have a region of analyticity, and you have another region where you have another analytic function. And then you can ask, are the two connected at all? Yes, they are connected from this. In this direction, they are connected. They are not connected in the other direction. So there is an irreversibility. So if you know the value of your diagram below the threshold, which is, for example, the Euclidean region, then, well, no prescription makes any difference. Then you know, by means of the diagrammatics I told you, how to go to the other region. But you cannot go backwards. And you do not see it here, because you say, well, I could go this way, but also that way. That's why I use the example of 3 dimensions, which is striking, because in 3 dimensions you have a square root, and a square root below the threshold is just a square root, and above the threshold, however, above the threshold, yes, here, the square root becomes purely imaginary. So here the square root is real, below the threshold, square root of some positive number. The square root of a negative number is imaginary. Well, there is no imaginary part in the bubble in 3 dimensions, so you have 0 in the fakeon case. So below the threshold you have the same, but above the threshold you have 0. And of course you cannot reconstruct anything from 0. So there is an unambiguous way to go from the Euclidean region to every other region, and that is how you compute everything you need with a fakeon prescription. But if for some reason somebody tells you, oh, I give you the amplitude here, then you don't know how to go back to the Euclidean region. And so you have a kind of analyticity that is region by region, and this has an implication on the violation of microcausality, because this fakeon prescription violates microcausality. Maybe that was already obvious to somebody of you, or not, but maybe I can emphasize it here, because if this is the propagator of a fake particle, this you can remember that it is also the average of the retarded potentials plus the advanced potentials. So if you have this kind of propagator, you have a violation of microcausality. At what scale? Scale is 1 over m. So at small distances given by 1 over m, you have this violation. So for example, if in quantum gravity we will see masses of the order of 10 to the 12 GeV, then you can work out 1 over m, and you will see that this is 10 to the minus 36 seconds, which is way below 1/1000th of a billionth of the smallest, shortest amount of time which we have ever measured. So that's how tiny the violation is with these masses. But if you have very light fakeons, then the violation can affect larger distances. And if you have massless fakeons, then violation of causality should be everywhere, and that's why fakeons should not be massless. Okay, so I think that this is enough for the diagrammatics, and I don't see what time it is. How much time do I have? Can somebody tell me?
Yeah, around 10 minutes or so.
Okay. So if you want to check the paper, you will find 2 loop diagrams, a box with diagonal 2 ways, and the same caveats apply, and the same identities apply, and to get to the proper decomposition. Now, an important thing is that this projection must also be performed in the starting classical action. The starting classical action is not the classical action. So imagine again for the epoch of ghosts. You take a gauge fixed action. A gauge fixed action as ghosts and gauge fixing. You do not take this as the classical action, of course. First you project, you eliminate things, and then you have to do the same here. And when you project away the fakeon, basically it is generating effective non-local micro-acausal self-interactions among the others, and since this green function contains the advanced potentials, that's where you violate microcausality, in interactions. And so it provides effective non-local, micro-non-local and micro-acausal interactions among the other particles. And that's...
Sorry, Damiano,
yes.
Let me clear up the story. You need a kind of action, or if you wish, which generates your vertices, because you have to have concrete Feynman rules to do your theory, right?
Perfect, yes.
Now, vertices, we can transcribe them into an action that would have normal fields and fakeon fields, right?
Yes.
That's, yes, if you wish, something to keep track of what are your vertices.
Yes.
Now, when you're talking about, so this is what defines your perturbation theory.
Yes.
Now, when you talk about the projection on the real particles, I presume you mean to construct the effective action in the standard way we describe the effective action, with sources only on the real particles and, yes, by integrating out everything. Is that what you mean? Yes,
perfect. So sources, okay, only on the real particles, you integrate the fakeons out. How? With this prescription.
Yeah, okay, okay.
And let me give you the example of gravity, for example. You start from quantum gravity. Let me add the cosmological constant for the normalization purposes. For cosmology, it will not be important. But anyway, you start from this action. Then this action has the Hilbert term, the cosmological term, yes, and the usual, let me say, Starobinsky term, and then there is a y squared. This is renormalizable, but it is not unitary if you quantize it a la Stelle or in those ways. It propagates 3 degrees of freedom. One is the graviton, mass 0, cannot be a fake. The other one is a scalar, inflaton. This one cannot be fake because otherwise you would not have inflation. So this is physical. But the other one has to be fake because it has a wrong sign in front of the kinetic term. And so if you quantize that as a fakeon, that means that this is not the classical action. This is just the one that provides you local, nice Feynman rules to do the diagrammatics. But then if you ask, what is the classical action? Well, classical action is the collection of 3 diagrams where you have physical external legs and fake internal legs, or no internal legs. So you integrate it out, and what you put there you put the 3-level propagator, which is the source of a small violation of non-locality, of locality and causality. Okay, so that's complicated because it's the true classical limit is not this, and it is not very explicit. I wrote a paper on that. Normally, when you make this projection, even at the classical level, you will find an asymptotic expansion. So your true classical action will be an asymptotic series because it carries remnants of the quantum theory it comes from. Another important point is that the construction I talked about fakeons works for...
Sorry, Damiano. And another question. If all the diagrams you're computing in order to construct the classical action are 3-level, why do you call these effects quantum? I would have thought that it's like integrating out classical fields whose propagators are not the standard advanced or retarded propagators, but they're more bizarre, right?
Yes, you can call it that. But you will see that it carries some remnants of the quantum theory origin they have. For example, because you generate very easy an asymptotic expansion. I mean, normally if I give you a Lagrangian, no matter how complicated or bizarre it will be, I'm not thinking of giving you just an asymptotic expansion. So that's just to tell you that If you ask me what is the projected Lagrangian exactly, I don't have it. So
no, I understand. But even if you integrated a normal classical particle, you will get an asymptotic expansion for what's left.
Yes, yes, probably yes.
Okay.
But in that case, you are doing something that you shouldn't do. I mean, you are doing something that because
fine. I agree
because a normal particle has boundary conditions, right? So you are losing the boundary conditions.
No. You can do it sometimes if this
here you have it.
Here
you have to do this because otherwise you don't have the classical action.
No, I agree. Yes. But I was just commenting on the non-polynomial nature of what remains.
It's non-polynomial, but also asymptotic. So maybe you will find that a single thing will have a coefficient which is an asymptotic expansion in some parameters. Okay. Every single one, not just the non-polynomiality of the thing. Now, this fakeon construction works under the assumption that you can have physical particles or ghosts, but not tachyons. So this is the reason for those two signs. These things cannot be tachyons. And if the signs are the ones I showed you, then the theory is not asymptotically free. This is known. I don't know if anybody wants asymptotic freedom. This is just a property of the theory, but Piva recently has shown that if you add matter multiplets of higher spin, then you can change the ultraviolet behavior of this theory. And in particular, a Palatini version of this theory can have a spin 3 multiplet, massive multiplet that in principle could change the ultraviolet behavior, and then you can have asymptotic freedom. I just commented at the end.
Sorry, Damiano. Yes? People usually say that you cannot, first of all, that you cannot add just one higher spin particle, but you have to add infinite, but I guess this has to do with massless stuff, right?
Yeah, exactly. Massless has to be infinite. Massive have to be multiplets. So what I showed is that you want a spin 3, if you want a spin 3 multiplet, at least you should have spin 3, 1 spin 2, 1 spin 1, and 1 spin 0, at least.
Okay, I see.
You can have more, but not 1 spin 3 alone, not 1 spin 2 alone.
Is that for the consistency of the fakeon projection?
And that is also for the renormalizability, because if you just have spin 2, this is Pauli fields, so it's not renormalizable. I want something that is renormalizable, thanks to the fakeon projection, that is unitary, thanks to the fakeon projection, but also renormalizable. And for renormalizability, I cannot have a Pauli fields or a Proca alone. For example, spin 1 should have spin 1 and 0. So I avoid the problems of the Proca one. But normally spin 1 and 0 is physical spin 1, ghost spin 0. So you have to quantize this as a fake, only this one. And then it works.
Okay.
So very briefly now on cosmology. In cosmology, you have the Starobinsky potential plus Weyl squared. Weyl squared, as you know very well, will not change the equations of the background. The Friedmann equations and the equation of the scalar will be the same. That part is the same. But it affects, crucially, the spectrum. And here inside you have this fakeon. So you know you need to do something to calculate things here, because it's also in a non-trivial background, not in flat space. Quantum field theory is in flat space, so this raises new issues. And I just flash the predictions here, and then I will tell you about the crucial point that is interesting to understand what happens. So you parameterize the fluctuations as usual. You work out the spectra with a certain attention to the fakeon projection that I will briefly mention in a moment. You compare the results with a certain data for the spectra, and you will find that the inflaton will have a mass close to the order of magnitude I wrote before, 10 to the 13 GeV. This is the scalar tilt. Now, a crucial thing is that the consistency of the fakeon projection implies this bound, as found in a paper by Piva, Bianchi, and myself, which forces basically the fakeon to be at least as heavy as this. So the spin 2 will be heavy also. And this is for the consistency of the fakeon projection. Now you have advanced and retarded potentials, yes, but in a background, so you have to compute them. It's a little bit of work, but not much. Then you go to high energies, and you see that high energies you get the behavior you expect, and then you interpolate down to low energies. High energies means subhorizon, and low energies here means superhorizon, for those who know what I'm talking about. But then you find that one of the two, this one, makes sense only if a certain square root is well defined. So it's the square root of a positive number, and that gives you this inequality. Otherwise, instead of an oscillating function here, you will have a hyperbolic sign that will make very distant regions of the universe interact instantaneously and non-locally, and so on and so forth.
Sorry, Damiano, but H is not necessarily M5, right?
No, but in this parameterization that I'm using, it's just M5 divided by 2. Yeah, I wrote H, but here I should have written M5 divided by 2. Sorry. Think of it as M5 divided by 2. Yes, H has no physical meaning indeed. So it depends on the frame and many things. What I want to comment here is this, that the crucial difference between inflation and particle physics. Because in particle physics, if you have something heavy, and this is heavy, 10 to the 13 GeV is very, very heavy. At low energies, like the superhorizon limit, you neglect it. You don't think that something heavy can affect predictions at low energies. Just decouple it, the Appelquist-Karazan theorem. But in cosmology, you cannot do it. Because in cosmology, to make predictions about low energies, you have to take care of the high energies. For example, you have to impose the Bunch-Davies vacuum condition, because you are on a background and you do not know what vacuum condition, how to quantize your system. And then you go to the high energies, subhorizon scales, and you hope that at high energies you have such a simple system, harmonic oscillator with a constant frequency, that you bet you know how to treat it, just because it is a harmonic oscillator with a constant frequency. Now, imagine if I have a ghost, as in this higher derivative theory with the C squared, which normally has a ghost. And then I have a ghost, a massless ghost at high energies. And I cannot make many assumptions on that region, because the high energy region is out of reach, observationally and experimentally. And so if I have ghosts, I have no clue. Although some people speculated about quantizing and putting Bunch-Davies conditions for ghosts, but they are harder to accept. And the Bunch-Davies conditions is also a disputed condition, because it is concerning a region that we do not observe. But at least if you have just a harmonic oscillator with a constant frequency, you can bet that it's just a common quantization of a harmonic oscillator with a constant frequency. Now, with fakeons, you have to be sure that you have just that and not anything else, so that the fakeon is fake everywhere and it is non-existent there as it is below, and this is the consequence. And because of that consequence, you have a sharp prediction for the tensor to scalar ratio, which I report here, which is this window here, and for the tensor tilt, just because of this inequality. So m chi should be at least m phi divided by 4. So it can go from m phi divided by 4 to infinity. You do not know the mass of the new particle, the fake. The data fix the scalar mass and the scalar tilt. You do not know anything about the other mass, it's free. But thanks to that bound, the entire range of values that remains is so unimportant for the tensor to scalar ratio prediction that you have a very strong prediction. Just it's less than 1 order of magnitude, the entire window. So you have two bounds now. One is the usual Starobinsky bound, and this is due to the projection that I told you. And so let's hope that numbers will confirm this.
How is the fakeon in this case affecting the scalar index?
Not much. Not much.
Not much means.
Let me see. Scalar index, nothing here, not much to the lowest order, but I can tell you that even if you go to the to various orders of correction, it takes, maybe I have the spectra. Let me see. No, I don't have them. I didn't put them. But
anyway,
here.
The question is that it's non-zero, but below today's error.
Yes. This is well below today's error. Today, I think that R is 0.0554, something like that. Yeah, it is. Can be possible. Yes. Okay. Let me conclude. So, purely virtual particles are based on a new diagrammatics. Their applications range from phenomenology and to quantum gravity and to cosmology. But the important thing that I wanted to focus in this talk was that they are based on a new diagrammatics, that they are completely perturbative. They do not advocate physical reasons to neglect particles like a decay, because physical reasons are powerful only when they apply. So there is always a region where physics will leave room for other options, as in the Leavitt case. The Leavitt models are good for if they work at higher loops, and nobody proved it, as an effective field theoretical approach. But here we want something fundamental. Now, what is the price to pay? The price to pay is small violations of microcausality and micro non-locality, in particular microcausality. And if the masses are sufficiently high, this is something well below what we have ever seen. And even if you boost, because some people tell me, but you can always boost the violation and make it larger. Yes, you can in principle, but the numbers are such that even if you boost it with the highest speeds of macroscopic objects that we can find in the whole universe, you will not get anything that we can appreciate. But of course, if you want to study models where you have very light fakeons, then things change and constraints may apply. However, we have already studied some phenomenological models, and we have seen that fakeons can evade various constraints of physical particles, and those constraints limit the applicability of physical particles, so they may be of use for phenomenology. In the case of quantum gravity, instead, they are necessary, because to make the theory renormalizable, it is necessary to add at least some higher derivative terms, and those bring in some things that need to be cured. In the usual approach, there would be ghosts. So in this approach, there's something different, and they are compatible with the optical theorem. But in that case, necessarily you have to do this. Otherwise, quantum field theory cannot offer you a solution. And with this, I think I can stop here. Thank you.